So we have collected some experimental data to look at the kinetics of some reaction of a chemical I'm just going to call X. So this is some data that I collected that we want to determine what is the order of X. This is a similar thing that we're going to see in the lab with crystal violet. I've just done it a little differently here, and I'm using Microsoft Excel to do the analysis. You're going to be doing all this within Vernier. It's going to be a little, you're going to have to do a little, it's going to be more clicking buttons as opposed to manually doing it like I'm going to do here. So we have what's going on here is we have collected over time, right, over seconds as they increase. We have some concentration data. So the concentration of compound X is what I'm calling it. And overall, we can see it's decreasing as the reaction goes. Now, the technique that I use is a little noisy. So there is some error to it that you're seeing. It bounces around the concentration, but overall, we're going to see it's going to decrease. And how does that kind of want to figure out what is the order? So the idea is we've collected the change in the concentration over time. That is reflective of what we'd call an integrated rate law, right? Over time, how does the concentration change? For a reaction with one reactant, these are the functional forms of the integrated rate law. It depends on the order. Is it 0th order? Is it 1st order? Or is it 2nd order? And we don't know what it will be for crystal violet because we don't know what the order is. So the idea is we're going to collect data, display it as if it was one of these, and see which one is a straight line. Because for the given order, if that is the order of the reaction, that equation will give us a straight line. So what I have right here is just concentration. So that'd be the same thing that we see in the 0th order equation. Logarithm of the concentration is 1st order, and the inverse of the concentration is what we use to test 2nd order. So let's go ahead and compute those transformations. So the first one will be the natural log of the concentration of X for time. And then we will also do 1 divided by the concentration of X for time. And I'm doing this one data point at a time. So what I do is I'm in Excel, so I can do calculations. So I type in an equal sign. ln means I want to do the natural logarithm, and then I say of a number. Well, I'm going to do the number right here. So I can click on that, close my parentheses, and hit enter. And so we can see in the kind of cell we've typed out, do the logarithm, but then it's displaying what the value of that is. So the concentration is 9.8. The logarithm of 9.8 is 2.28, whatever. And we want to do that for each data point. So in Excel, there's that green box in the bottom right corner. If I double tap that, it will drag down or copy basically my calculation into all these other cells for all the other data points. So if we look right here in this cell, it's doing the natural log of the concentration at time 13 to give us the log of the concentration at time 13. We can do a similar idea here for our inverse. I can do type equals 1 divided by and click on the concentration, hit enter, and then that is what I have right there. Again, drag it down, and I can get this, cell right here or whatever. At time 22, it was 7.14 was the concentration. 1 divided by that gives me 0.14. Good to go. I got it all set up. So this is the transformed data. I will then take this and make graphs of each particular set of data. So the first one I've got is the concentration versus time. So go ahead and insert that. Got a scatter plot for that. Move that up here. Okay, so this is if I look at just the concentration of X over time, I can see it decreases, which makes sense. It should. It's a reactant. Then I want to do the natural logarithm. Get that. Insert a graph. Okay, so I got natural log. And I need to do all three always. I don't know what it's going to be. And then 1 over X, insert a graph for that. Wonderful. So I've got my 3 graphs now. Just the data, the concentration versus time, the log of the concentration versus time, and then 1 over the concentration versus time. And basically the idea is only one of these should be a straight line, right? And whichever one is the straight line tells me the order. So I can look and see concentration versus time. That definitely is not a straight line, right? We can see there's the bow to it. Log of X versus time also looks a little bent. 1 over X versus time looks pretty straight. So that's a good sign. Now, this is kind of an eyeball test. This is subjective. I'd prefer something a little more objective, right? Like, how good is it? So what I'm going to do is I'm going to add trend lines. So what I'm going to have to do, I'm going to have the computer fit a straight line. So what I'm going to say right here, for example, this is the concentration of x versus time. So what I'm doing is I'm basically saying, make me a line like that. Get me the line that kind of best goes through this data, that's a straight line that kind of captures the change in concentration versus time. So what I'm going to do is I'm going to add a trend line. You can see there's that dashed line in there now. I'm going to display the equation, and I'm going to show r squared on the chart. Okay, so I've said, okay, when it's concentration of x versus time, that's my kind of trend line that I get. And I'm going to do this for all of my lines. So now I've got it for log of x, natural log of x. I'm going to move that to see it. And I'm going to do the same thing for my inverse, add a trend line, display the equation, display the r squared. And you can see here kind of what we saw before really is made clear by the trend lines. We can see that in the case of the concentration, that the trend line, the line itself, the data kind of wraps around the trend line, implying it's not a straight line. And then in the logarithm x, it still is wrapping around the trend line. That dashed line is a perfectly straight line, and the data is wrapping around it. Here, in the inverse, the data buries the trend line, right? The trend line is kind of a narrow line. That's kind of a font thing or a display thing. You could adjust it to be thicker, but it's hidden, right? It's completely hidden by this data, implying that that data is covering a pretty straight line. Numerically, we can also evaluate this using what's called the r squared term. You can see it's shown for all of these. R squared values from 0 to 1. Whenever we do this sort of fitting, r squared tells us how good the fit is. How close to a straight line is the underlying data. In the case of the concentration, it's not very close, right? We get 0.78, not very good. In the case of the natural log, we get 0.94, 95-ish, which would be normally very good. But if we compare it to 1 over x, we get the 0.99, 97. That's really good. That implies that this data is very much a straight line. So if we want, so what this is telling us, that if we want to generate a straight line, we need to take 1 over the concentration of x versus time. That is always true of a second order, right? If we had started from knowing that our equation was second order, we would use the inverse form of the equation. And so we kind of are doing the opposite here. It's not a straight line when you just plot the concentration versus time, and it's not a straight line when you plot the natural log versus time. So that means that this underlying reaction is not 0th order or first order, but it is a straight line when you plot the inverse of the concentration versus time, telling you this is a second order reaction. So that's what we can do here. You're going to do a similar thing, Crystal Violet. The actual calculations and like fit will be done within the Vernier software and where you collect the Logger Pro data. But it's all the same idea. You're trying to fit the line, see how good the line, a straight line is at representing the kind of collected experimental data and what that tells you about the order of the reaction.